Stop making a face. I'm not making a face.
No, I don't know. Sure.
All right. So guys, the main idea behind that sheet I gave you with this on it was the idea that if I draw a probability distribution out and I make it so that the whole area is 1, then any question about an interval in the middle of it will be related to the area of that section. It's kind of nifty. So let me to get us into what we're going to be doing today. If I have a normal distribution, of course that looks like Now, I have in the past had students that were just so incapable of doing this, I just had them do a triangle.
That's me.
Low, high, low. I mean, you just need something. And if you're smart, you're going to be a student who draws this picture for a lot of the problems because it's a nice anchor. It's a visual check to make sure you're thinking about things correctly. Do you have to draw the picture? No. Is it good to draw the picture? Yes. So if I have a normal distribution, can somebody tell me, whatever the mean is, what percentage of the data is below the mean? Yeah, because the mean does what? Cuts it in half. Because if it's normal, if it's exactly perfectly normal, it's got to be perfectly symmetric. Right? Now watch, this is kind of cool. This is going to be related to the chart we're going to use. Old-fashioned, crazy-ass Jeff doesn't like us getting answers out of technology because we're less connected to it then. If I had a chart that told me the areas below z-scores, so for example, if I looked up in the chart -3, and what it tells me is the area below it, is that going to be a very big number? No. The area below this? No, it's not going to be very big. That means, what does this mean? What does that -3 mean? What do I mean by that? What's the mean?
3 standard deviations.
Yeah, so the mean is 0. So that would be 3 standard deviations below the mean. Should there be a lot of stuff outside of there? No. In fact, what do we officially call 2 standard deviations away? Anything outside of there is unusual. Shit, right? Now, here's where things get interesting. So what we just say, we said that anything outside of 2 standard deviations away we consider unusual. Anybody remember the numbers related to that? What percentage is within 2 steps away? 95. And there, that means there's 5% outside, which means there's how much below -2? If that's 5%, this is 2.5. So this should be 0.025, roughly. For example, right? So as I move up this, so below -3 should be a very small number. And then as I move up, I keep getting more and more area below me. Does that make sense? So whatever this is here, it's going to definitely be bigger than -0.025 negative. I love that shit. And they are areas, they are probabilities, so they can't be negative. So as I move along, and once I hit here, of course, what percentage is below that? 50%, so 0.5. And so above this should be 0.6, 0.7, 0.8, you know. Now where is it going to be changing the quickest? Where is that number going to be changing the quickest? Is it changing very much down here? There's not a lot going on here. Is it changing a lot in here? Oh, hell yeah, because it's very tall. The minute I move over a little bit, I just picked up a big chunk of data. Because most of the data is close to the mean. So think about heights. If you saw a dude that was 5'8", would you freak?
No.
You would freak. What the? Why?
You're short.
I'm 5'8".
Excuse us.
I'm 5'9".
Shit.
We're average size.
All right. So don't compare them to your own height.
No.
Amazonians. Right? Would you be freaked out that you saw a dude? Now, if you saw a dude that was 4'2",
Yeah.
because they would be down here. Right? I'm not picking on the 4'2" people. I'm just saying there's not very many of them out there. Heights are known to be normally distributed. So most people will be close to the average height, and then as you get further away, there's less and less of them. I like it. So the whole idea of what's unusual is actually kind of nice. It has a physical meaning. What would be weird to see? Well, if I'm talking about heights,
7 feet.
somebody like 4 foot, somebody like 7 foot, the extremes. If I saw somebody close to the average, that's not weird. Yes?
It's a guy's not gonna try that. It's a guy's not gonna try that.
Okay, sorry. All right. Okay. So, whatever chart this is, it actually, the way I read it is when I look up a z-score, when I look up a number of steps away, a z-score, it tells me the area that I've got below that as I move through this. So then I can find any areas I want to between any two z-scores or so forth just by playing with the numbers. Okay. So that's what the other side of this is all about. Okay? Is how to use a normal distribution to figure out probabilities. So what's really, really beautiful is what a big chunk of statistics is when can I say a distribution is normal enough? So we're going to see a few situations where we're like, well, if it meets this condition, it's normal enough. If it meets this other condition, it's normal enough. Why is that important to know? Because if I know it's normal enough, that means I'm allowed to use the sheet that's got all the frickin' answers to every question imaginable. If I don't know it's normal enough, oh shit, that's stats too. Yes?
So in general, when you're looking at like some data, the smaller you have, like when we were looking earlier, but like 6, like a 4, 1, like 6, 3, 1, is because it's such a small set of data that wouldn't really be considered normal necessarily. But
Yeah,
you
it's
have
too small.
A large set of data, even if it's like skewed a little bit to one side, it's
Yes.
still basically normal.
And you do have, sort of like we have this idea of what's unusual or not, right? We do have, like I said, we do have conditions that things have to meet, different distributions, in order for them to be normal enough. Normal enough to do what? To use this, to get all the answers. If they don't meet those conditions, I can't use this, I got to get the answers some other freaky way. Yes? We're going to find out. And again, we can actually figure it out. Who remembers within one standard deviation, there's what percentage for normal? 68%. Which means how much is outside?
The rest of it.
Beautiful. I love that. And you're like, you didn't say to be specific, Jeff. You're right. 68% inside, so there must be 32% outside, so there must be 16%. So below -1, there should be roughly 0.16. I say roughly because those numbers are rounded just to make it easier to remember. Yes?
Sorry for my weird question, but is like figuring out, not necessarily what we're going to do in this class, but figuring out if it's normal enough, is that related to like the formula of the Gaussian curve and all that? Is it using that?
Normally, no.
No?
You don't have to go to that. Sometimes, of course, yes. But normally not.
Okay.
Yeah. All right. Let me give this to you. Don't freak out. Let me just give this to you, and then we'll talk about how to read this shit, and then we'll do some problems using this. Okay.
I'm like, I don't want to do the math. The rest of it.
People hyperventilate
I
as you
freaking
see
know.
this thing. Before too many of you get this in your hands, do not write anything else on this besides maybe your name. You're going to use this for tests and quizzes, and you're going to turn it in with those. And if there are notes on this thing, that is not a good way to be. Everybody with me? Okay. You don't want to lose this sucker. I'll bring a few extra copies, but not like a ton. Yes?
Huh?
I do.
Where's my rainbow? Who's texting me now? I get it. Brandon, you can't write anything on it, bro. I'm just kidding. You can write your name. It's a joke.
Huh? One more. Oh, this thing? Hopefully I got one for you. This thing.
No, the chart.
The chart, okay. Uh-huh.
I just need to start. What? Or not? You just gave us a paper. This is
All right, cool. Can somebody turn off the one that says whiteboard, and then the one that's diagonally away from it? All right, let's take a look out. All right, first off, let's look at the chart by itself. Let's recapture this number, and also the one that we got for -1, which below it was supposed to be about 0.16, right? Figure that out. 68 in, 32, 16. Did that one earlier. So if I look at, here's how this chart works. This is a little bit like, well, it's not like anything. But here's how if I wanted to get -1 exactly, you see how this is the first decimal place and this is the second. So I can't remember if I said this to everybody, but z-scores, we normally round them to 2 places because the chart we're going to use, this one, only goes out to 2 places. So if I want to look up -1.21, I would go -1.2, 1 right there. See, this is 0, 1. -1.21 is right there, for example. So don't go -1.21, this is 1.20. So what do I want to look up right now? -1.00. -1.00. 1587 rounds to be 16%. -2.00. We said about 2.5%. That's, it's not too far off. I like it. So see how they're not changing very much back here. Look, they're not changing at all way down here. Why are they not changing at all very much down there? Because there's very, very little stuff down there. So as I move, I'm not picking up a lot. But the closer I get to the mean, the more stuff I'm picking up, the quicker it kind of changes. That's another reason why I like you to use this chart, to get you used to how the probabilities kind of flow through this thing. All right. So let me see if you guys can just look at the chart correctly. Can you tell me the area below -2.37? Z-score of -2.37. Yes. So -2.3, -2.37, yeah, 0.0089, I love it. So that means, as you move, if you get to -2.37, you've got 0.89% of everything below you. I like it. So if you got on a quiz or a test, your z-score is -2.37, that means you're not quite in the first percentile. Right? You've only got 0.89% of the people did worse than you, if it's normally distributed. Who's got a question? Let me make really sure you understand. When am I allowed to use this to get probabilities for a problem? When it's normally distributed. Where does the chart actually tell you the answer to that? With the normal curve it's got printed at the top, right? This only works if it's normally distributed. That's what these numbers relate to. So it's not uniform. Do I need a chart for uniform distribution? No, I can just calculate the dumb areas myself. This is the stupid thing where, if I draw a little segment in here, what's the area of this? Do I have an area for a curvy top thing? No. And like I told you, that's what calculus does really well. It finds an area below stuff. Most of us haven't taken calculus, so we had a computer actually do the calculus and give us these numbers. Okay, I like it. Maybe. So, let's do a couple more things before I unleash you on this worksheet. What's the probability that a z-score is bigger than 1.26? So notice there's a whole other side. So first off, try to draw this. Draw this. Draw the picture and shade in the area that I want. Draw this picture. So it's going to look like, well, it always goes right in the middle for z-scores. So what goes in the middle for z-scores then? Zero. I like it. Because z-score is how far away from the mean you are in standard deviations. Of course, the mean is 0 away from itself. Aw. 1.26. It doesn't matter if you're perfect. Just put it up there somewhere. So where's the area that this is asking for? Yeah, above that, right? So this area, right? This is the picture that you should draw to help you do a problem. Now, what do you get when you look up 1.26? What do you get?
48962.
And the minute you use this chart to get an area, you should put it in the correct place on your picture. What do I mean by that? This chart is very single-minded. It only tells you areas that are
Given.
Normal.
where? Below the z-score you look up. So when I look up 1.26, I get 0.8962. Where is that on the picture? It's all this.
Oh.
Areas go up there. Z-scores go down here because z-scores look like areas. That's evil. 0.12, is that a z-score or an area? I don't know. So be nice to yourself. Z-scores down here, areas up here. Now, this is not the answer to the question. How do I get the answer to the question? 1 minus this, exactly. I don't want this side. I want the complete other side. I want the opposite side. So 1 minus 0.8962. That is just a physical idea. The whole thing is 1. This side is 0.8962. So what's the other side? 1 minus that. And I don't know, have I told you guys the... Let me just tell you this, just so you know. And if you don't give a shit, you got your calculator, that's all I have. If I do 1 minus any decimal less than 1, I can just think, what makes 8 become 9? 1. What makes 9 become 9? 0. What makes 6 become 9? 3. What makes the last thing become 10? 8. Of course, you're like, well, the calculator got that to me. Put your shot. Can't beat me. Right. Now, somebody, let me stop right here. Yes? Looking at 1.26. Right? If I can get, so looking at 1.2, 6. So that's the area below. That's the only thing the chart knows is the area below the z-score I'm looking at. So if my question involves something other than that, I better adjust that number.
Is it always going to be 1 minus that?
Don't say that. I don't. There are other situations where I have to do other things. But basically, if it says greater than, you are going to have to do that, sure. But don't try to generalize it. Don't try to memorize a bunch of situations. Just look at it. It just takes like 3 seconds to figure out what to do.
So what's the mean?
What's what? What's the mean?
0.
0. I love it.
So then 0.
Because what am I talking about? Z-scores. What's the mean for z-scores? Always 0. I like it. So we're going to talk about what if I have a normal distribution, but I know the mean is 28 million and the standard deviation is 13 million. You know, I can change those into z-scores. Don't I have a formula that makes them become z-scores? I have a formula that can change x into z. Is that correct? In fact, we call it, amazingly enough, we call it the z-score formula, right? Because we're crazy. And if I know it's normally distributed, I can then use the z-score chart once I've made them into z-scores. I love it. Well, what's this problem all about? It is just z-scores. That's all it is. Yes?
For example, what if it was negative 1.26?
Okay, now wait a minute. Are you getting a little ahead of me? Maybe. There's a shortcut. You can save like 2 seconds. Can everybody look real quick? Look up negative 1.26. What do you notice? Yeah, now why does that make sense? Because this is the answer that I want, Isn't this area the same as the area that would be below negative 1.26? All right, so it's sort of like using your blinker. Don't use this shortcut unless you really know when it works. If you're not sure, don't use it. So like, don't use your blinker if you're not used to using it because you're one of those idiots that just leave it on, or that change lanes with the blinker going the other way. Yes?
If we change the question to, we're looking for the anything bigger than negative 1.26, the answer would be 89.
Oh my gosh, it works.
Yes, because you would do 1 minus 0.1038, of course.
Oh my
Yeah.
gosh, that makes so much sense.
It's my favorite phrase. All right, let's try another one together before you do this worksheet.
0.8315, that's what I got for this. Oh man.
What about this question? The probability that negative 0.12 is less than z is less than 1.18. Like it. So the probability that z is between negative 0.12 and 1.18. So if you're not sure how to do this, at least draw the picture, label your z-scores, shade the area, and then try to figure out how you would do this. I love it when somebody's like, well, last semester we would have just put those numbers in the calculator. Maybe that's why you're taking it again.
You do less than, right? So before.
Always have somebody that's like, my professor let us just push buttons.
Oh, you're doing this problem. That's okay.
What if your numbers don't live to scale?
What is it?
If you don't draw the numbers to scale?
Doesn't matter. It doesn't matter. As long as the numbers are in the correct place. I love it when somebody puts negative 0.12 over here. That freaks me out. The middle is 0 for z-scores. Negative 0.12 better be over there. 1.18 better be over there. And beyond that, it doesn't matter where it is. This is supposed to be a quick visual check to make sure the answer kind of makes sense, or that you can label it so you can see what to do. So anybody know what to do here to get the exact answer? Yes?
You find the 1.18 and then you also find the other one and then subtract.
I love it. So if you look up 1.18, the answer to that's going to be too much, right? Because when you look at 1.18, it's the area below that all the way down forever. But I want to stop here. So if I look up the area below negative 0.12, I can just subtract those areas and I end up with the area in the middle. I love it. So what do you get when you look up 1.18?
0.9699.
Yeah, 1.18. You get do it again. Yeah, 8810. I like it. 0.8810. That means there's 88% of the data is below at 1.18. If your z-score on a test that was normally distributed is 1.18, you're a little bit better than the 88th percentile. Because 88% of the data would be below you. 88% of the other students made less than you. That's the connection to all this other stuff we were doing this semester. Now what's the area below negative 0.12? I like it. 0.12. 0.45. No. 22. Negative 0.10. Negative 0.11. Negative 0.12. Get used to that right now.
Like 2 left.
All right, there's 2. So 0.4522. So what area is in the middle here? 0.8810 minus 0.4522. 0.4288. I like it. Sweet. So that almost 43% would be between those two z-scores. like it. You might keep. All right. So now you can group up with other people if you want to. I want you to work on that. It's the other side of that binomial sheet. On the reverse of this sheet are the normal things. I drew them all for you already. Just so you get used to having them there, so maybe you'll do it for yourself. This sheet here.
Can you do percentile or percentile?
Close to it. Yeah. I know. It's not quite the first standard deviation.
It's close to it though?
It's close to it. Yeah. But it's interesting where it is. Oh, okay. I like that one. So can you draw that situation? Do you see how the end of this answer right here, if that was the question, just less than that was a percentile.
So it's opposite?
So now I'm giving you the percentage and asking you to work backwards to find the z-score. Yeah. Whenever you look anything up in the chart, it's always below what you just looked at. Always. Understand it? Exactly. So then you just gotta make sure, oh look, they do ask for less than, so that is the answer. If they ask for greater than, you gotta do 1 minus that, because it's the opposite of what I want.
Everything is less than that. If it was eating a Z, that's everything
Well, less
greater
than.
right here.
The beautiful thing about the inequality symbol is if your variable's on that side, it points in the direction it's one. So it's pointing that way. It's over there, yeah. It's not greater than, it's less than.
Mine shows also.
Well, that's what the chart always tells you. The question could be greater than, which means it wants the other one. Yeah. Well,
Oh, yeah.